Hello everybody. So in this module we will continue with the design of the lead compensation and see what are the techniques or how do we place the poles and the zeros. Earlier we had a little formula to place the zero, but we saw that zero by itself is not realizable, so we need to add a compensating pole. Okay, so let's start slowly with this analysis. Right. So what we concluded from the previous lecture is that, well, this is the compensating zero and I should have a pole for practical reasons to realize this. And we also knew why the pole should be to the left of 0. Right. So what we will now try to answer is where should the 0 be and how far left should the pole be from the 0, and that will actually lead to some nice exciting observations. Okay, so before we proceed, we will see how we can realize or construct the lead compensator with help of some basic circuit elements. So it turns out that if I take resistance R1, R2, C1, I apply a input voltage and measure the output voltage across the resistors R2, which are connected in this way. So VO, the output voltage, by VI, which has the construction of a 0 and a pole with these numbers, and these numbers can be computed directly, right. So where alpha here is R2 over R1 plus R2, and we clearly see that this is less than 1 and tau is R1 C1, and this alpha being less than 1 ensures that the pole is to the left of 0. Okay. So this is how we will construct a lead compensator, and this guy, you know, okay, this guy will have some angle contribution, some gain contribution and so on, right, because there is some dynamic element here in terms of C1. Okay, so now how does this look like, right? So if I look at the sinusoidal transfer function of the lead compensator, it looks something like this. I have alpha here, I have 1 over j, 1 plus j omega tau and 1 plus j omega alpha tau, just rewriting this in the sinusoidal form. So this guy goes here, this guy goes here and so on. Okay, so when alpha is less than 1 for low frequencies, the compensator provides a gain which is less than 0 dB. So if I look at the Bode plot here, and if I were just to draw with a regular alpha, my plot would start somewhere from, not from 0, this is a 0 dB line, my plot would start somewhere from here depending on the values. Okay. And this is not really desirable because a control system is essentially a low pass filter, and I really do not want the low frequency signals to get attenuated, right. So this low frequency things I should preserve, and therefore what I do is I just add a gain of 1 over alpha and call VIT as the output of the controller, where my compensator now becomes this one, and the alpha thing is gone now. Okay. So when I do this, my Bode plot now starts at the 0 dB line, or an absolute gain of 1, and it increases this way. Okay, I should also be careful that I do not, so I would not want to attenuate the low frequency signals, and at the same time I also would not want to amplify the high frequency signals. So a trade off would be to select this alpha smartly enough such that this is preserved, whereas this length here is not big enough. So I have to maximize this alpha in such a way that the high frequency signal attenuation is as minimal as possible. And just look at the phase plot, right? This will, we were always talking of a phase lead, right? So this is the phase lead that it provides. So this guy, it is adding an angle, right, this thing here. Okay, we will do a little bit of more of where to add this angle and all this when we do the frequency design compensation, but at the moment it is, we will just concentrate on this thing here and what to do with this alpha. Okay. So it is desirable to have alpha as large as possible so that this length is as small as possible, which means the high frequency signals are not amplified beyond the reasonable limits. Okay, now we come back to design. So a warning before we do this design procedure is that if I follow the procedure, it is not guaranteed that I will get the exact solution. I will be very close to the exact solution, after which I may have to do a little bit of trial and error just to maybe just shift the pole slightly to the right or the 0 to slightly left and so on. Okay, so this is how the construction looks like. Okay, so given a certain performance specification in terms of the peak overshoot and the settling time. So again, just to remind ourselves, these are all transient response specifications, right? I am improving only the transient response. What will happen to the steady state is something which we will see parallelly as we go through these steps. Step 1 is again find what are the dominant poles given MP and DS. Okay. Now step 2 is in designing a controller is plot the root locus and see if there is a gain k which passes through this SD. If it passes through the SD, then it's perfect, right? I don't really need to do much, but usually it does not, as we saw in the previous example, right? So we'll again start with the same example and see how we go about constructing a compensator which looks like this. Okay, so this is what we had in the example in the last lecture, which MP being 10% and settling time being 5 seconds translates to closed loop pole locations at these numbers. Okay, so the angle deficiency is obvious by this computation, and we know that we now conclude that the root locus should be pulled to the left. And so. Okay, now earlier construction just focused on this 0, right? So we didn't have a P. Okay, now what changes when we have this P here, right? So first, okay, let me just say that this is at some arbitrary location ZC, and PC is some arbitrary location. What I know is just the phi. This I have already computed from here, right? That the compensator should provide an additional angle of 28 degrees with this formula. It also done in the previous lecture. So I know this guy. This is 28 degrees something. This theta is cos inverse of the desired damping. So the location of ZC now depends on where is where is this gamma. For example, this phi, when I say that the location that this is may not be unique, if I just choose a ZC here and you just draw a line here, okay, I can just add some number phi, the same number, right? If this is say 25 degrees, I can add 25 degrees, and I will say that this is also a PC, right, which also gives the same phi. There could be several possibilities, right? If this is my SD, ZC, PC with phi could even be, well, this is ZC, much further PC and so on. This is also phi. This is my 0, this is my pole. So, well, now what is a good location? Because there are infinite possibilities of ZC and PC which gives me this lead. Okay. Now let's see, let's draw a line from here till here, this is the omega n line, and call this angle gamma. Right, we see that the locations now depend on how much is the angle gamma, right. So for a given gamma, right, so this I can use this phi, this theta to write down these formulas with the omega n. I will not really derive these formulas, but given this configuration, this angle is phi, this is gamma, this is theta, and an omega n. ZC is related to gamma, theta, and omega n via this formula. PC is related again to omega n, gamma, theta, phi via this formula. So what is this is unknown, because my problem is where to place ZC, where to place PC. On the right hand side, well, omega n is known, theta is known, phi is known. What is unknown is this gamma. So the location of poles and zeros depends on this gamma. So gamma is the deciding factor. Okay. Now let's just arbitrarily select few gammas and check. Okay. So let's see what what is important when we choose this gamma? First and the most important is the dominance condition, second is the gain k, third are the error constants, and 4 is the alpha, right, because here we wanted alpha in such a way that this length here from here till here was as small as possible. Okay. So let us just do again some trial and error. Start with gamma 1 of 15. Take this gamma 1 of 15, I put in these formulas and I get appropriate locations of zeros, right, and the pole. Let us see that the pole is fairly to the left of 0, so that condition is trivially satisfied. The gain k is 1.4, the velocity error constant is 0.5, alpha is small enough 0.423, and the settling time is 9.23 seconds. Okay, so with these numbers what we see is okay, the gain is 1.4, the velocity error constant has decreased from 1 to 0.5, which means the steady state error increases. Alpha has some number 0.423, which is less than 1, and it is again trivially satisfied. Settling time is really poor, right. What I want is a settling time of less than 5 seconds. Okay, why does this happen? Say, well, even though my lead compensator is successful in giving me this lead, or this ensures that angle of GC times G is minus 180, why are these things really bad? The errors have increased, settling time is bad. This is something to do with the dominance condition, right, that the dominance condition is not satisfied, which is obvious from these plots, right. So this is what we would like to design. We would like our closed loop system to behave, but actually it behaves like this. Of course, it is a little strange behavior here, that there is no overshoot, but there is still a little, it goes down and then it results something like this. The MP criterion is met, but we are not really happy because that is not just the objective. Your settling time is fairly large and the errors have increased. So gamma equal to 15 is a wrong choice, even though this is satisfied. Okay. So this plus this is not the sufficient condition. Okay. So why is this happening? Why is the dominance condition failing? Because very close to the closed loop poles is a 0, right, and that is here, right. So if you look at, so this guy, so how did we define the dominant poles? That they should be here, such that, well, there is nobody sitting over here and the other guy should be like further away from some limit. But here, well, there is this 0 here, which loses, or which helps losing the dominance, right. So these guys are no longer dominant, and therefore even though the root locus passes through SD, now this is very important, the root locus is actually passing through SD, but the settling time is not guaranteed because these are not the dominant poles anymore, because there is this guy sitting over here, right, and therefore this combination does not work even though the root locus is passing through this point, because the nominal design what we do is just for a second order approximation, this one. Okay. Okay, let us choose another number. Gamma is 50.2, right, gamma is 15.2, then I get some, with the same formulas I get some location of the 0, some location of the pole being to the left of 0, and it's kind of quite good, right, that the velocity error does not change much, alpha is good, and well, the peak overshoot is more or less which I wanted. It was 10% was the desired, now I have 11%, settling time is fairly good enough. Okay, and you see that, well, some kind of dominance is ensured because both this blue and the black lines are very close to each other. So this works well, right. I say this is actually something nice for me, right. Okay, now I become a little greedy and say that from 15 to 50.2 I could get this blue and the black lines close to each other. Now let me get a little more greedy and say, well, I will choose this 65 degrees. Okay. again the same phi and all would be ensured. I choose gamma 1 to be 65 degrees, then the 0 comes at minus 1.4, pole comes at minus 2.3, and some so this certain gain. The velocity error constant has changed again from 1 to 1.3, and the alpha has now decreased from 0.6 to 0.6, right. Okay, so now let us look at the numbers. Well, the peak overshoot is not really good, right? It's 13%. It's actually slightly increased. Settling time is still okay, right? It's 4.27 seconds. And you see that the dominance is slowly has started. It's the system has these poles have slowly started to lose the dominance, because well the distance between the the blue and the black curves is increasing. Okay, so why is this happening with the increase in gamma? Okay, so now let's look at what is happening with the location of the poles and zeros, right? So in the okay, in the previous case, the value of gain k at 1.89, which results in the closed loop poles to be here, here and here. You see that the distance between the pole and the 0 here for this value of gain k is very minimal, in such a way that they actually cancel out each other. So the closed loop system will just have like two poles, one pole here and one pole here. That is like dominance is ensured by these two being very close to each other. Ideally, we would want these to cancel, these two guys to get cancelled, but then that will possibly happen only in the limiting case when k is very large. So for this value of gain k, these are my dominant poles and these are very close to each other. So they will almost nullify the effect of each other. Whereas in this case, I see that there is some distance between these two, that these don't cancel out each other, and they in some way affect the performance, or they contribute to the plot here, to the step response. And therefore we see that as the distance between these two again increases, the distance between these plots also increases, right. So this is a little nice thing happening here, a nice observation, that for this gamma the effect of this pole 0 pair is the minimal. Okay, now is there really a method of finding, right, what is a good choice of gamma? I just cannot do a trial and error all the time, right. So, and if we look at the relation between gamma and alpha, first case I had gamma of 15 and alpha of 0.4. Gamma of 50, alpha increases to 0.62. Gamma of 61, alpha starts decreasing. So there is one gamma which maximizes the alpha, and this is the gamma which I am interested in, right. And maximizing alpha is also good for me in terms of the attenuation, okay. Because if you see, this is 4.45 dB here, this is 4.06, this is 7.47. So this is, I want, as I said earlier, I want to keep this length to the minimum. So a good gamma is the one which maximizes alpha, right. And not only that, this also provides or helps me satisfies the dominance condition, right, in such a way that the transient specifications are met, okay. What is the effect on the steady state error? We will not really worry about that, but some adjustments can be made to accommodate steady state requirements. So here I am I would primarily be interested in just improving the transient response without having too much effect on the steady state. As we said, see how you saw here, right, the effect on the steady state is not really too much. There is some effect, but we could possibly try and keep this to a minimum. Okay, so now the gamma was the variable, so in this expression for ZC, gamma was unknown, PC gamma was unknown, right, and alpha is related to ZC and PC, right, from the construction of the compensator. Let's go back to that slide and say, well, how is ZC and PC related via alpha? Here, right, this is ZC, this is PC, right, and ZC over PC is 1 over tau 1 plus, sorry, there is no 1 plus, 1 over tau, and on the denominator I have 1 over alpha tau. So, this is Zc by Pc is alpha. So, how to maximize this? So, alpha, which is Zc by Pc, alpha is now like like as some nonlinear function of gamma. Then I can just use standard calculus, what calculus teaches me, that the maxima occurs when d alpha by d gamma equal to 0. I do all the computations and I get a gamma. This gamma maximizes the alpha. Now, the unknown, when I was computing the location of the zeros and the poles, were the gamma. Now, I get the gamma in terms of theta and phi. These two are known to me. So, now I know where to place these poles and zeros, right, given a gamma. Okay. So, I just do the computations as before. I get that start from theta, I find what is theta from cos inverse of zeta, I get how much is the gain, and then gamma turned out with that formula to be 50.2 degrees, exactly as what we had guessed in the second guess of ours, which has a good alpha of 0.62. Okay, and okay, these plus are exactly the same as what we saw, right? That the poles and zeros are very close to each other, so they nullify each other's effect, and these two guys then ensure the dominance of the closed loop. So, this is exactly what we had before, right? So, what we have answered here so far is how to place the Zc and Pc. First is that the angle of Gc should be phi. Now, next is there a unique location? Well, the answer is no. The Zc and Pc were depending on the gamma, and we chose the gamma in such a way that it maximizes alpha. Right? So, that is method 1, and it gives us some beautiful results here. Okay. Now, if I am really lazy to go through all this calculus, and is there another method of doing this? Well, it's a nice graphical method that I know the location of SD, right. So, this is SD here, right. And then okay, I know theta, I know omega n, I just draw a line to the left here, right, and what I do is I bisect this entire angle, right. I draw a bisector to this angle, which is this one, right. So, this is the bisector, right, and then I know phi, right, phi is derived by these computations. So, what I do is I go phi by 2 to this side, right, draw a line, this is Zc, I go phi by 2 to this side, draw a line, and this is Pc. This is exactly the same as what we had done before. All that analysis which we talked in terms of maxima and minima would lead to the same thing if I would just do this bisector thing. So, there are two ways of understanding this, right. So, this gamma which I obtain by this geometric method actually maximizes alpha, as we saw earlier. Okay. Now, method 2, is there another way, right? If I really do not want to compute gamma, I forgot the calculator to the exam and things like that, well, what could I do? So, what we had seen here is the following, right. So, look at again these distances, this and this, and things were depending on how these were located from each other, right. So, from this observation I can say that in cases where an open loop pole is in the region below the desired pole locations, right. So, this is not really far, right, this is 0.8 and this is 1. In cases where the open loop pole -1 is in the region below the desired locations in the close vicinity of it, then I just place a 0 just slightly to the left of that pole, right. So, here I have a pole at -1 and I place the 0 just say at 1.07. Right. Once I know the 0, I can easily calculate where is the pole just based on the phi or the lead angle which it should contribute, right. So, this also provides desirable value of alpha while guaranteeing the dominance condition. In our condition, this is kind of easily, if you see here, this is kind of met easily, right. So, this 0 is placed slightly to the left of this -1. I would not want, you may even ask why not instead of 1.07 place it at 0.93. If I place it at 0.93, so this pole according to the root locus condition will move towards the right, and I do not want anybody to move to the right. So, to ensure dominance of these two poles here, so I want them to go to the left. Okay. But this is a very restricted condition only in this case. In the case where an open loop pole is placed just slightly, just in the vicinity, just below this dominant closed loop pole. Okay. So, so now I found out what is the ZC and what is the PC. Now, the unknown now is what is the closed loop gain K. This I could easily find by the root locus magnitude criterion, right. Use the magnitude criterion to find the gain K at which the root locus passes through the desired closed loop poles. So, we could see also what is the effect on the steady state specifications, even though that is not really the objective of this controller, right. And if the error constants are close to the specifications, we can just do some minor adjustments, right. So, in our example 1, where the locations of 0 was at 1.07, pole at 1.7 resulted in a gain K of 1.889. This can be computed by the magnitude criterion. And this is very straightforward, and we had also seen the formula for this. Kv was 1.1 per second, right. The steady state requirement here is not met, right. Then can we actually do a minor adjustment of the lead compensator? Well, this can only provide a minimal, some very small adjustment, but that can somehow even alter with your peak overshoot and all. So, in those cases where we want to alter both the transient and the steady state, we would also look at what we would call a lag compensator, which we will study this lag compensator in the next lecture, right. So, before we finalize the design, we just check with simulations to verify if all the criterion are met or not, right. So, where did we start with? We started with specifications in such a way that MP was less than 10%, settling time was less than 5%, and I do all the design, choose the best alpha, it gives me 11% of MP and 4.38 seconds of the settling time, and these are kind of within acceptable limits. So, I could just summarize the design process into the following steps. First is find the dominant poles. Second is check the gain condition, just go through the root locus and check is there any value of gain K such that the dominant poles lie on the root locus. If no, then I consider a lead compensator and then calculate where to place the poles and the zeros. Next step is to calculate the gain K, right, and then see is there too much effect on the steady state error constants, right. If they are, then I would go further. I would go for a further design procedure which would also include a lag compensator, and I would verify all this design by appropriate simulations to see if all these specifications are met or not. If not, then I could just slightly push my pole or zero slightly to the right or left to see that the appropriate specifications are met. So, in the next lecture we will see how to meet specifications on the steady state error or the error constants via a lag compensator. Thank you.